Chapter 8, Vectors. 8.1 is geometric vectors. The magnitude of a vector is the length of a directed line segment. The direction of a vector is the directed angle between the positive x-axis and the vector itself. So one important thing that you should know for the final is that two vectors are only equal if they have the same direction and magnitude. So an example we're going to show you is the triangle method. So in this example, you're trying to find the resultant of 2v minus 3w. And so first, you need to draw a vector that is twice the magnitude of v, and then that will represent 2v. Then you draw a vector from the opposite direction to w, and then after that, you 3 times its magnitude to represent negative 3w. Finally, then you place the initial point of negative 3w on the terminal side of the 2v vector, and then this is called tip-to-tail method. Then you finally draw the resultant from the initial point of the first vector to the terminal point of the second vector. So the resultant is 2v minus 3w. Algebraic vectors. Vectors can be expressed algebraically as well. And how? Well, you use ordered pairs or real numbers. So in this example, we're going to write an ordered pair that represents this vector using points 2, negative 3, and minus 4, 2. So first, we're going to represent vector xy as an ordered pair. So the formula for this is x2 minus x1, comma, y2 minus y1. And our x2 here is minus 4, and x1 here is minus 2, so negative 4 minus 2, and then comma 2 minus of 3. So finally, you would get the ordered pair of negative 6, 5. So if you want to find the magnitude of the vector xy, you have to take the square root of x2 minus x1 squared plus y2 minus y1 squared. This is also the distance formula. And you plug in the same values as you did before. And then the magnitude is square root of 61. So the ordered pair for this vector is negative 6, 5, and it has a magnitude of square root 61 units. So there's another example that's very important to know, and that's adding and subtracting and multiplying vectors. So here we're going to use vector s, that's 4, 2, and vector t, that's negative 1, 3. And so in example A, we're going to add these vectors together, and this is simple. So you add the x's together and the y's together, and you got 3, 5. And then in example B, you do the same thing as the addition problem, but you subtract the x's and the y's, and you got 5, negative 1. And for C, you're just multiplying 4 times the coordinates of s. So that would be 4 times 4, 2 in the parentheses. So that would result as an ordered pair of 16, 8. And finally, example D is using multiplication of vectors and addition of vectors. So first, you're going to multiply 3 times s, the coordinate of that vector, and then you are going to add the result that you got from multiplying to the other vector, and then finally you get the result of 11, 9. One more thing we need to learn is to write a vector as a sum of unit vectors. So here we're going to use, again, m as 2, 2, and p as 5, 4. So first, you need to write the ordered pair, and that's going to be 3, 2, and you do it the same way as I told you before. Then you write a vector mp as the sum of unit vectors. One important thing you need to know before is that a unit vector in the direction of a positive x-axis is represented by I vector, and a unit vector in the direction of a positive y-axis is represented by a j vector. So vectors are represented as ordered pairs, and they can be written as sum of unit vectors. So in our example, 3i is going in the positive direction of the x-axis, and 2j is going in the positive direction of the y-axis. So the sum of our unit vectors for MP is 3i plus 2j. So 8.3 goes over vectors in 3-dimensional space. Like we did before, the ordered pairs, but now we're going to learn about ordered triples. Like ordered pairs, they can be used to represent vectors. Operations on vectors represented by ordered triples are similar to those on vectors represented by ordered pairs. So for example, for the distance between 2 points in a plane, you need to find the distance between 2 points in the space. Each point in space corresponds to an ordered triple of real numbers. To locate a point P with coordinates x1, y1, and z1, you need to first find x1 on the x-axis and then y1 on the y-axis, and the new thing here is the z-axis, so you have to find z1 on the z-axis. Then you find the planes that are perpendicular to the y, z, and x-axis, and then y1 and z1 respectively. These 3 planes will finally intersect at a point P. So an example would be using coordinates -1, 3, and 1. We're going to locate -1 on the x-axis. That's the normal way you would use it to graph, and then 3 on the y-axis. But one thing that you have to remember is the x is the diagonal axis shown in the graph here, and then y is the horizontal axis, and z is the vertical axis. So you would put -1 on the the vertical axis, and then 3 on the horizontal axis, and then 1 on the diagonal axis. So then you just draw the broken lines, and then you form a rectangular prism, and then the planes intersect at -1, 3, 1. Writing the sum of unit vectors. Write AB as a sum of unit vectors for A, 5, -2, 3, and B, -4, 2, 1. So first, you need to express the vector AB as an ordered triple, and then you need to write the sum of unit vectors. So I is the x coordinates, j is the y coordinates, and k here is the z coordinates. So -4, 2, 1, -5, -2, 3. So finally you would get the coordinates -9, 4, and -2. So you would write this as -9i plus 4j minus 2k.
Okay, 8.4 is perpendicular vectors. So we're going to let A and B be perpendicular vectors and let vector BA be a vector between their terminal points as shown. Then the magnitudes of vector A and vector B and vector BA must satisfy the Pythagorean theorem. So we're going to use BA squared equals vector A squared plus vector B squared. Now we're going to use the definition of a magnitude of a vector to evaluate vector BA squared. So first we're going to do vector BA equals the square root of A sub 1 minus B sub 1 squared plus A sub 2 minus B sub 2 squared. And after solving, we're going to finally get to vector BA squared equals A squared plus B squared minus 2 A sub 1 B sub 1 plus A sub 2 B sub 2. If vector A and vector B are two vectors, A sub 1, A sub 2, and B sub 1, B sub 2, the inner product of A and B is defined as A dot B equals A sub 1, B sub 1 plus A sub 2, B sub 2. So the first example is to find each inner product if U equals 5, 1, and V equals -3, 15, and W equals 2, -1. Is either pair of vectors perpendicular? So for problem A, we're going to do 5 times -3 plus 1 times 15, and that will equal to 0. So if it's equal to 0, then they are perpendicular. So U and V are perpendicular. And for letter B, V dot W equals -3 times 2 plus 15 times -1. And that's going to all equal to -21. So since it's not 0, they're not perpendicular. Okay, so example number 2 is find the inner product of vector R and vector S if vector R equals 3, -1, 0, and vector S equals 2, 6, and 4. Are vector S and vector R perpendicular? So we're going to multiply 3 times 2 plus -1 times 6 plus 0 times 4. And we get 0, so their inner product is 0, so they're perpendicular. So the formula we use to find cross products of vectors in space is A cross product of B equals, and the whole formula is right there in the blue box. And unlike the inner product, the cross product of two vectors is a vector. This vector does not line the plane of the given vectors, but is perpendicular to the plane containing the two vectors. So for example 3, we're going to find the cross product of V and W. If V equals 0, 4, and 1, and W equals 0, 1, and 3, verify that the resulting vector is perpendicular to V and W. So after using that formula, we finally get 11I minus 0j plus 0k. Or we could write it as 11, 0, 0. And to find the inner products, we just multiply those. So 11, 0, 0 times 0, 4, 1, we get 0. Since the inner products are 0, the cross product between V and V times W is perpendicular to both vector V and vector W. 8.5 is applications with vectors. Vectors can be used to represent any quantity such as force that has magnitude and direction. Velocity, weight, and gravity are some of the quantities that physicists represent with vectors. So an example is, suppose Jamal and Mike pull on the ends of a rope tied to a dinghy. Jamal pulls with a force of 60 newtons and Mike pulls with a force of 50 newtons. The angle formed when Jamal and Mike pull on the rope is 60 degrees. So on the right we have a diagram here from the word problem, and that's letter A. And let F1 and F2 represent the two forces. So B, determine the magnitude of the resultant force. First, find the horizontal, x, and the vertical, y, components of each force. Given that we place F1 on the x-axis, the unit vector is 1i plus 0j. Therefore, the x and y components of F1 are 60i plus 0j. F2 equals xi plus yj. So we're going to do cosine 60 equals x over 50, and we get 25. And sine 60 equals y over 50, and we get about 43.3. Thus, F2 equals 25i plus 43.3j. Then we're going to add the unit components. So we're going to do 60i plus 0j plus 25i plus 43.3j, and we get 85i plus 43.3j. So the force is going to be about 95.39 newtons. C, determine the direction of the resultant force. So we're going to use a tangent ratio. So we're going to do inverse of tan times 43.3 over 85, and we get about 27 degrees. So the resultant force is 27 degrees with respect to the vector on the x-axis.
8.7, modeling motion using parametric equations. So some vocabulary is projectiles are objects that are launched, and trajectory is the path of the projectile. The range is the horizontal distance traveled, and vector is magnitude and direction. Gravity acts upon the vertical direction. The horizontal component is unaffected by gravity, so the horizontal speed is constant throughout the distance traveled. 8.7, horizontal and vertical components of initial velocity. This is an example, so it's find the initial horizontal and vertical velocities of a soccer ball kicked with an initial velocity of 33 feet per second at an angle of 29 degrees with the ground. So the first formula you would be using is vector v x equals vector v cosine theta, and the next formula you'd use is vector v y equals vector v sine theta. And if you plug in both of those numbers from above, you'd get 29 and 16. And then the path of the projectile is launched from the ground may be described by the parametric equation, which is x equals t theta vector v cosine theta. For horizontal distance, you use y equals t vector v sine theta minus 1/2 g t squared. for vertical distance, where t is time and g is acceleration due to gravity. You use g would be about 9.8 minutes per second, meters per second squared, or 32 feet per second squared. 8.7 is horizontal and vertical velocity. So a rock is tossed at an initial velocity of 50 meters per second at an angle of 8 degrees with the ground. After 8.8 seconds, how far has the rock traveled horizontally? First, write the position of the rock as pair of a parametric equation defining the position of a rock for any time t in seconds. So you use the equation for that is y equals t vector v sine theta minus 1/2 gt squared, and you also use x equals t vector v cosine theta. So then you find x and y when t equals 0.8 seconds, which is 39.61 and 2.43. 8.7 parametric equations for the path of a projectile above ground level. The parametric equation describes the path of an object that is launched from ground level. Some objects are launched above ground level, then you must add the initial vertical height to the expression for y. This accounts for the fact that at time 0, the object will be above the ground. 8.8 Transformation matrices in three-dimensional space. Basic movements in three-dimensional space can be described using vectors and transformation matrices. Recall that from a point at xy in a two-dimensional coordinate system can be represented by the matrix xy. This idea can be extended to three-dimensional space. A point at x, y, z can be expressed as a matrix x, y, z. An example of this would find the coordinates of a vertex of the pyramid and represent them as a vertex matrix. So it's A is -2, -2, -2, B is +2, -2, -2, C is 2, 2, -2, and D is -2, 2, -2, and E is 0, 0, 2. So the matrix for the pyramid is shown below. Thank you for watching.